All right. Well, I'll get started here. May begin with a word of prayer. So, dear Heavenly Father, we thank you for this morning. I thank you for the students. Just ask that you guide our steps. We thank you for your mercy and for your forgiveness for us, for your shed blood on the cross. And just pray be with us this day, that you guide our steps, Lord. In your name I pray. Amen. All right, so let me start with an example. This is a question. Is there a question about anything? Okay, so example it is then. So suppose we want to solve the inequality, let's say x squared plus, I don't know, 7x minus 2 greater than 0. All right, suppose you want to solve this inequality. This one's a little bit uglier than the ones we did last time, because this one I don't think we can factor nicely, right? Can you factor x squared plus 7x minus 2?
No.
Yeah, I think 2's got factors of like 1 or 2, and so you're going to get what? Like a cross term of, well, you can't get 7. So what we're going to do is complete the square on this thing. So here we go. X, what's half of 7? I mean, it's 7 halves, right? So you square that thing, all right? And then to be fair, we subtract 7 halves squared, right? So this thing I'm doing right now is known as completing the square, right? And then, of course, the minus 2, it's still there. All right, so just to reiterate, what's going on here is I'm taking these two terms, x squared and 7x, and I'm expanding them as a difference of these two terms as well, right? So if you multiply out the terms in red, you get back to the terms I underlined in red, all right?
So when you do the difference of squares, you're always like going to divide it by 2.
Yeah, I always divide by 2 the coefficient of whatever's on the x term. Unless, of course, your leading coefficient of x squared wasn't 1. If it was 2 or something, then first you probably want to divide by 2. These kind of problems, yeah? Okay, so then what? Well, we need to clean this up and make it look a little bit better. And so I think the way to do that, this is what? This is 49 over 4, right? Minus what? So let me just do a little arithmetic over here. 7 halves squared is 49 over 4, right? What's 2 in terms of fourths? It's 8, right? So we have 49 plus 8, which is 57 over 4, right? Greater than 0. Now, if you don't see that right off, you are allowed to use a calculator in here, right? Non-graphing, scientific calculator, but calculator nonetheless. And certainly, most of these things, capable of adding fractions. Now, I would say you really would like to have a calculator which can add fractions. If you got one that just does decimals, you're not really quite where you want to be in terms of a calculator resource, Just saying. When I use 49 over 4 plus 2, it gives me back 57 over 4, right? Or I could do parentheses, 7 divided by 2, close parentheses, square that thing, add 2, and I still get 57 over 4. So if your calculator can't do those things, and you also can't do those things, you probably need to get a different calculator, right? I like this one, Casio FX 115. Of course, other people like the, what's it called there? TI 30, something like that.
So you got negative 57 over 4 by minus 49 over 4 by 2.
Yep, because 2 is, 2 is what? 8 quarters, right? So now we look at that as that. Just think about it, turn it into a square, and with that little move right there, now we can factor because it's a difference of squares. And so the factoring works out like this. This is x plus 7 halves plus the square root of 57 divided by 2, x plus 7/2 minus the square root of 57 divided by 2 greater than 0. Right. So I should mention, excuse me, this thing I just did here, all right, these steps, collectively, I would call this factoring via completing the square. Okay, so if I was to ask you on a test or quiz or something to factor by completing the square, this is what I'm talking about, right? Now, why do I want to do that? Because once I do that, it becomes clear what the critical numbers are for the expression. What are the critical numbers for this expression? We either have minus 7 plus the square root of 57 over 2. I mean, that's the first one's actually minus the square root of 57 over 2, right? But this one would come from that, yeah? So I'll do some underlining here. This factor gives me that critical number. Gives me that critical number. And this factor right here gives me this critical number. You might recognize these numbers that you're looking at as solutions to the what? This is what the quadratic formula would give you for this quadratic, right? So that's another way you could find the critical numbers, right? But if I ask you to factor by completing the square, I do need you to be able to do this, right? So not trying to tell you that the quadratic formula is an end run around completing the square. I do want you to learn to complete the square in here. All right, so anyway, moving on here. We are following that roadmap I set out last time, right? The 4-step, remember our 4-step plan for solving nonlinear inequalities? Step number 1 was to identify the critical numbers. It took a little effort to do that for this example, but we did it. Those are the critical numbers. Step number 2, right, is to draw the number line and put the critical numbers in order. Which one comes first? Yeah, the -7. Well, they've both got a -7. But is it the minus or the plus one that's coming first here? The minus, yeah. -7 plus the square root of 57. Is this positive or a negative number? Square root of 57 is what? It's bigger than the square root of what? 49? Square root of 49 is 7, right? So this is about like 7 point, I don't know, 7 point whatever, 7.5-ish. And so the one with a plus is in fact a positive number, right? And as such, we know that 0 is somewhere between the critical numbers, right? So I'll make a little notation here, critical number. There's a 0 here somewhere, all right? And as such, we can evaluate the expression at 0 and see. We're now into step 3 of the roadmap, right? We're trying to write pluses and minuses as appropriate to each case, all right? So like the middle case here is where 0 is. We plug in 0. What happens? You get, well, -2, right? That's negative, so I put minuses here. Now what? Now what? Well, these are both power 1 and power 1, which means we flip signs at both critical numbers. So we go from minus to plus here. And we go from minus to plus over here as well. All right, now I've now completed step 3 of the roadmap, right, for solving a nonlinear inequality. And so now I can read off the answer. So the answer is, solution set is what here?
How did you figure out whether it's going to be positive on the number line or negative?
So I plugged in 0 for the middle case, right? And then I used the sign flip. The sign flip theorem, which says that if your critical number corresponds to a factor with an odd power, you flip signs. Listen, I'll do another example which illustrates the sign flip thing more times. The next example will be more ugly in that regard, okay? But here, solution set is minus infinity to minus 7 minus the square root of 57 over 2. That's half of it. And then union minus 7 plus the square root of 57 over 2 all the way to infinity. And there you go. That is the answer. That's the solution set to this inequality. Here, let's look at an uglier example. All right, so let's suppose we had x to the 4th minus 81. All right. And then we'll do, let's say, x squared minus 4x plus 3 divided by, let's see here, how about x squared plus 4x plus 5. And then, let's say x plus 10 to the 3rd power. And let's figure out where that is less than or equal to 0. Find the solution set to this thing. All right. So, kind of like example 1, this one it requires some algebraic treatment before we can really find the critical numbers, right? Because what we're facing here, these factors are not yet factored, right? So let me just deal with those. And tell you what I'm going to do here is I'm going to deal with each one of these factors separately, and then I'm going to put it all together, okay? So let me deal with them one term at a time. So I'll focus our attention first on x to the 4th minus 81. How does that factor? See, that's x squared squared minus 9 squared, and as such, that is the difference of squares. So that's x squared plus 9 times x squared minus 9, right? Now here it's important to factor completely, because if you don't factor completely, you can't really see what's going on. Now x squared plus 9 is already factored completely over the real numbers. That's prime, right? Can't break that down further without complex numbers. But this x squared minus 9, that factors again, yeah? So this is x squared plus 9 times x plus 3 times x minus 3. All right, so we have, that's it for this term right here, okay? That's that. Next up, x squared minus 4x plus 3. You guys can do that one, right? There was a problem like this in your first week's homework, right? Actually, a couple of them. How does this factor? What we got? Yeah, it's going to make me do all the work. X plus 1, x plus 3. Almost right. But when we multiply that out, what do we get? We get a 4 with that. So what do you need? It's easy fix, right? Yeah, just make those both minuses, right? Now we've got it. Minus x, minus 3x. So there, that's how that factors. Can you guys factor the next one? How about x squared plus 4x plus 5? One of my favorite quadratics. It just works out nice, that one. What do I mean? Ooh.
X plus 4 and then x minus 1.
So I heard x, what did you just say? You said x plus what?
4 and then x minus 1.
But multiply that out, what happens? If we multiply that out, we get plus 4x minus x. We get a plus 3x in the middle. But I think one of you said 5 and 1, right? Also, somebody said 5 and 1. 5 and minus 1 or 5 and plus 1? 5 and plus 1, right? Because you got to get 5 over here, right? But that gives you 6x. That didn't work. If we put both minuses, that also doesn't work. Everything we're trying is not working. What should we do?
Plus 5 minus 1.
Again, that doesn't work because that will give you minus 5 here, not plus 5. I mean, so like, if you fix the middle term, you lose the last term. If you fix the last term, you lose the middle term. You know?
So is it unpackable?
Right, yeah, this one's prime.
Okay.
And in particular, we can see that by completing the square. Completing the square is easier here than it was in example 1 because here we just have 4 as the coefficient. So the completing the square looks like x plus quantity what squared. We take half of 4, which is 2, right? Now, completing the square says you have to subtract the square of that half number. So I have to subtract 2 squared. The 5 is still there. And clean this up, what you've got is x plus 2 quantity squared plus 1. Which shows it's prime. If you can write the polynomial as a sum of squares, that means it's a prime polynomial. In this case, prime quadratic, I should say. How about x plus 10 cubed? That one's already done. Nothing to do there.
So
Resist the urge to multiply that out. That is not a good use of your time. Yeah.
So why did you do the minus 2 squared? Like in that alternative?
This is completing the square. So we take half of this coefficient, right? We add it to x, we square that, and then we have to subtract the square of that number again. Now the reason for that, since you're asking, I mean, fine question, is if we multiply this out, we get what? We get x squared plus 4x plus 4, right? So the thing is, we started with these two terms, right? When we write this down, what have we done? We have put something there that wasn't there before, the 4, right? So in order to be fair, we also have to subtract the 4. In so doing, this is equal to that. And then the 5 just rides along. So this is how I think of completing the square. I always think of it as I make a square and then I make a correction. All right? Other people like to think about adding things to both sides of an equation, but I don't think that's a good way of thinking because sometimes we don't have an equation. Sometimes we have an inequality. Sometimes we're just trying to manipulate one side without doing anything to the other. And sometimes it's part of a larger story, so I really can't add something to the other side, right? It's important to be able to complete the square on a isolated factor like this. Right. Anyway, okay, I digress. Okay, so there we go. We have, now what have we done? We have understood how to break down that expression. Now let's break it down. Let's write it again. I'll write it over here. So example 2 continued. So we have, as it turns out, x squared plus 9, x plus 3, x minus 3, right? And then what was that one? X minus 1, x minus 3, right? All divided by what? X plus 2 quantity squared plus 1. and then x plus 10 cubed, right? We want that to be less than or equal to 0. One more step before I leave this. We should make sure when we're doing this kind of thing, if there's any kind of commonality between the different factors, right? Like this and this. See that? We can combine those. So what we really have here is x squared plus 9 times x plus 3 times x minus 3 squared times x minus 1 divided by x plus 2 squared plus 1 times x plus 10 quantity cubed less than or equal to 0. All right, there we go. Stick a fork in it. It's done. All right. Now we can assuredly identify all the critical numbers without accidentally like repeating them or something. What are the critical numbers here? So do you get a critical number from x squared plus 9? You can tell from my question the answer is no, right? So this is prime. In order for that to be 0, you need x is plus or minus 3i. We don't allow complex numbers, okay? In this discussion, we're looking for real solutions at the moment. X plus 3, could this be 0? Sure, that gives you minus 3. This gives us 3. This gives us 1. X plus 2 squared plus 1 is prime. The solution to that being 0 corresponds to the complex number minus 2 plus I, or minus I. Those are not allowed. We're looking for real solutions. And then finally we have minus 10. All right? So we've got 4 critical numbers in this case. Now we draw our number line.
So why did 9 walk as a critical number?
Let me call this thing Pac-Man. What's that?
So why didn't number 9 not work as a number for you?
Oh, because if we put 9 into if we feed Pac-Man 9, it does not give you 0. Because putting 9 into this does not make that 0. It makes it 18.
Oh, yeah.
I mean, the difference is this is x squared plus 9. Yeah, I mean, this is x squared plus 9 versus x plus 3, right? So the difference is I plug minus 3 into this linear factor, 0, right? I plug 9 into this, oh well, right? X squared plus 9, again, is 0 for x equal to plus or minus 3i. Right? But that is outside the scope of this discussion because when we're solving inequalities, we're looking for real solutions. The complex numbers don't allow for less than or greater than. Those are outside this discussion. Okay, so here's my number line. I need to put the critical numbers in order. Which one comes first? Negative 10. Very good. Which comes next? Negative 3. And then 1. And then 3. These don't have to be, like the distance here doesn't have to be accurate. It doesn't matter, all right? This is just a guide. We're really just keeping track of pluses and minuses in each case, all right? So I always start with 0 if it's not a critical number. If 0 is a critical number, then you got to pick something else for your initial test point. But 0 is a nice choice here. It's not a critical number, right? So I can choose 0. Where does 0 fit? Which one of these cases? Where is 0 in this? Between negative 3 and 1, that's where 0 is, right? Very good. And so feed Pac-Man 0, right? What do you get? You got to think through it, right? We get like 9 times 3 times minus 3 squared times minus 1 divided by 5 and then 10 cubed. Now the value of the number doesn't really matter for our current purpose. It's really just the sign we care about. So if you look at it, we've got plus, plus, minus, divided by plus and plus, which is altogether a minus. So it's negative in here. in that case. Now the sign flip theorem says we can propagate those signs to other cases by paying attention to the order of the factor corresponding to the 0. So we look at this, all right? Let's look at minus 3 first. Where does minus 3 come from? Why is it here? Minus 3 is here because x plus 3 is up here, right? This x plus 3 factor is 0 when we put x equal to minus 3. X plus 3 is to the power 1. That's odd, which means we flip the sign, going from here to here. All right? How about this? Minus 10. Well, minus 10 is right here, right? Again, it's to the third power. That's odd. We flip the sign. So we go from minus, makes me go from pluses to minuses over here like that. All right? Looking at minus 10. Next up, 1. What happens at 1? Do we flip signs or not? Well, at 1, we got what? Where's 1? Where's this 1? Why is this here? This is here because there's an x minus 1 factor there, right? That's an odd power. Again, we flip the signs. All right. Then what? How about 3? Where's this 3 coming from? Well, this 3 is coming from this x minus 3 squared. That is not an odd power, right? Square is an even power. That means we do not flip signs. We just keep the same sign. We go plus to plus. Right? Now, if you're wondering why there's this sign flip theorem, here's just a preliminary explanation for you. Think about this versus this. We'll talk more about this after like the test, I think. Well, I mean, we might do some of this next week. I can't remember, but the full discussion of graphing is like the second third of the course, I think. But check this out. So here's y equals x cubed. Here's y equals x squared. Just to try to explain to you the sign flip theorem briefly. All right. So this is the third power. This is a square. What happens? Third power crosses. Second power bounces. That's why the sign goes plus to plus. Right? And it's the same if you look at like, you know, linear term, y equals x looks like this, yeah? Y equals x to the 5th looks like this, right? Y equals x to the 4th looks like this. X to the 6th looks more like that. X to the 8th looks like a football. If you zoom in, the goalposts almost, I mean. Anyway, my point to you is even powers bounce, odd powers cross. And that's why we have a sign flip theorem. Roughly, I'm cheating a bit, but. Okay, now we've completed step 3 for example 2. And we can write down the answer, right? We have to think about it though. What's the answer here? Can I erase my Pac-Man step? You guys okay if I erase the Pac-Man step? Wait a second, okay. We're good, okay.
So did you flip the sign with -10 and that's how you make a positive?
Uh-huh.
Okay.
Yeah, I mean that's, well I started with the red and I propagate, this is what I plugged the point in. And then from that point I work my way to the left and to the right. You can always plug in another point and decide whether it's positive or negative by plugging a point in. It's just very time intensive to actually plug numbers into this expression, right? It's much easier to just use the sign flip theorem. Anyway, all right, so we're looking for less than or equal to 0. So what's the solution? So we got minus infinity to minus 10, all right? And then where else? We've got unioned with minus 3 to 1. And is there any other minuses? Nope, pluses everywhere else. Now I'll ask you the question, should we include or exclude minus 10? Does minus 10 get included in the solution, or do we not want minus 10 actually in the solution? We want it excluded, right? Because it gives you division by 0, which is not permitted. So we must exclude minus 10 because that x plus 10 to the third power is in the denominator, all right? How about minus 3? Include or exclude? We want to include it because we're looking at less than or equal to, equals to 0. We're interested in that, so we include the minus 3. All right. How about 1? Again, 1 is in the numerator. That gives us a 0 for the expression. We're looking for zeros, so we include that thing. All right, that's the bulk of the answers. Sometimes you have an isolated point. Now we've got to think through this, right? What are the zeros? Which numbers make the expression 0? I would point out these 3 right here, right? These guys make Pac-Man equal to 0, right? The minus 10 is the one from the denominator. So all 3 of those should be in the solution set if we're looking for places where it's 0. We have 2 of them, right? We're missing what? 3, right? So we have to union with the set just containing 3. Now, if you miss this, if I was to assign this a quiz problem or something, you had all of this, but you didn't have that, I'm still probably going to give you a lot of credit, like 90% credit. All right. Wait, there it is. So obviously there's a lot of moving parts to this example, right? I think we're pretty much putting into play everything we learned last class. And some of the things we learned week 1, or reviewed week 1, right? So one of the main differences today is that I have, I've leaned further into the issue of completing the square could come up as we're doing the algebraic preparation for these problems, yeah? So, my shirt is starting to get eraser dust on it. Eventually I have to wash this thing. But, all right, can I erase? Okay. All right, let us move on then. Next up, absolute values. So, have I talked about absolute value last class? I don't think I talked about absolute value at all last class, did I? Okay, good. I should tell the students who want me to go slower just to come to the 8:15 section, because I find myself going slower in here whether I want to or not. So absolute value, here we go. Now you may not feel like I'm going slow. So absolute value, here's the definition. Absolute value of x. It's the square root of x squared. All right. That is equal to plus or minus x, depending on what x is. In fact, in particular, it's minus x if x is less than 0 or equal to 0, and it's x if x is greater than or equal to 0. In fact, the cases agree at 0, right? Some of you doubt me, so let me just show you an example. Absolute value of like minus 6 is the square root of minus 6 squared, right? Which is the square root of 36. You can get out your calculator, punch it in. What you'll get back, 6, right? And so you're like, well, okay, I knew the absolute value is minus 6 is 6. I still don't understand why the absolute value of x is minus x. Well, think about this here. In this case, 6 is what? It's minus a minus 6. So that's how the formula works in the interesting case, yeah? I think the possibly confusing thing here is that our intuition tends to want us to think that if we see minus x, that's a negative quantity, right? But is minus x a negative quantity? I would say depends, right? I mean, if x is positive, then yes, minus x is negative, right? But if x is negative, minus x is in fact positive, right? Here, x equals to minus 6. Minus a minus 6 is positive, right? So we have to be careful thinking about sign of variables, right? Okay, so critical feature here is that one of the critical features is that the absolute value of x is greater than or equal to 0. That's actually pretty much the key feature of absolute value is just that right there. What are other properties of absolute value? I'll just mention this right now. We have that the absolute value of x times y is the absolute value of x times the absolute value of y, right? You can prove that the absolute value of a product is the product of the absolute values. And just another warm-up comment here. What happens if we take absolute value of minus x? What's that? So minus x is really what? Minus 1 times x, right? So if we apply the property right above, we get absolute value of minus 1 times the absolute value of x. What's the absolute value of minus 1? One, right? So this is just absolute value of x, right? So, all right. What's another thing you could say about absolute value? I probably should mention this. We'll need it in a second. I would say this, and the absolute value of x is equal to distance of x from 0 on the number line, right? What's another word we use for the absolute value of x? We call the absolute value of x, here as an example, 1,000 and minus 1,000. They both have magnitude what? 1,000, right? Absolute value is also called magnitude sometimes. It's the size of the number without regard to the plus or minus, right? So, I mean, the magnitude of a positive number is just a positive number, but the magnitude of a negative number, you strip the minus off, right? Which is absolute value. So another way to look at this equation I just wrote here, right, is that x and minus x, right, they're the same distance from the origin, which is just a kind of silly comment, but it's true, right? X and minus x are the same distance from the origin on the number line for any x. Okay, so there's more you can say about absolute value, but there's a quick just reminder, this is absolute value, all right? So let's look at an example, and I think this will be example 3. And let's suppose we want to solve the absolute value of, let's say, 7x plus 2 equals to, I don't know, 5. How would you solve this equation involving absolute value? So, yeah. Okay, go for it, yeah.
7x plus 2 is 5, and then 7x plus 2 is -5.
Right. Or, very good. That is, in fact, one way we can do it. So let's complete that thought. So we isolate 7x both times, right? So by subtracting 2 on both of these, right? So we get 7x equals to 3, and 7x equals to minus 7. Divide by 7, we get x equals to 3/7, or x is equal to minus 1. There you go. Them's your answers. Perfectly good way to do it. Very good. Very good. Let me show you another way to do that same example. But first I'll just pause. Is there any question about that? So I like, what was your name again? Gabrielle. I like Gabrielle's method. I mean, I think that's a good method that works well for most students. Here's another way. If you like this way, you can also use this way. The other way would be to use the plus minus notation. So if we have absolute value of 7x plus 2 equals to 5, we could also solve this like this. 7x plus 2 is equal to plus or minus 5. So that means that 7x is equal to plus or minus 5 minus 2, which means that x is plus or minus 5 minus 2 over 7, right? And that gives us either the following: x equals to 5 minus 2 over 7, or x equals to minus 5 minus 2 over 7. So of course that's 3/7 or minus 1. Right. So if you like the plus or minus notation, you can use it. If you'd rather break it into 2 cases, you can use it. It's really up to you. Yeah. People are like, is it really better? I'm like, well, I don't know. I mean, this is 45 seconds of writing. This is 30 seconds of writing. This saves you 15 seconds. But if it confuses you, it's not worth it, right? So if you're completely happy here, you understand this perfectly, keep with this, right? If you like it, use it. If you don't, whatever. Unlike completing the square, like completing the square was something you need to learn. This is just a convenience. Okay, here's another one. Suppose we're looking at like the absolute value of 3 minus 10x, yeah, equal to 17. Can we solve this equation? I will use Gabrielle's method. And so here we go. 3 minus 10x equal to what? Yeah, 17. Or 3 minus 10x equal to minus 17, right? All right, I'm going to write down my steps this time. So what I'm going to do is I'm going to subtract 17 and add 10x to both sides. Let's see here. Over here, I'll add 17 and add 10x. The algebra goes a little bit different. So that gives me a minus 14 equals to 10x. That one gives me 20 equals to 10x. So I can divide by 10, right? So divide by 10. What do we get? Minus 14 over 10. Let me just simplify. This would give us x equals to, what's 14 over 10 is what? 7/5? So minus 7/5. Or over here, x equal to, well, 2. 20 over 10 is 2. So in all of the examples we've worked here, example 3, example 4, example 5, what can you tell me? Describe the solution set. What was it? Was it an interval? What was it? I mean, it's not an interval. Like most of the intervals that you can think of, they contain, when I'm talking about the interesting intervals, the ones that contain infinitely many points, right? Like 0 to 1 or 1 to infinity, any of those. They contain infinitely many points. In these, all three of these examples, there were 2 solutions, right? So the solution set has a pair of numbers. Now, do absolute value problems always have a pair of numbers for their answer? So yeah, there's another possibility, right? The number could be repeated. Like here's a silly one, a very silly one. Well, I mean, it's not that silly actually. Okay, fine. Absolute value of, I don't know, 2x minus 3 equals to 0. What are the solutions to this? See, if you put a 0 over there, the 2 cases become the same case, right? So you're solving what? You're solving 2x minus 3 equal to 0. Or 2x minus 3 equal to minus 0. The 2 cases become one case, right? And so the solution is just what? 3/2, right? So there's just one solution there, right? What else could happen? How about this? You've got absolute value of 3x minus 17 plus 2 equal to 0. Solve that thing. If you dare. Well, if we rearrange this, isolate the absolute value, what do we got? We've got absolute value of 3x minus 17 equals to minus 2. At this point, stop what you're doing. Don't go further. That's impossible. I mean, you could ignore the reality that that's impossible and go forward and like write down Gabrielle's equations, right? But That would be a bad idea, because this does not have a solution. Why? Because the absolute value is non-negative, right? But this equation here says that the absolute value is equal to -2. You cannot have this, right? So when you go and solve the equations that you might try, you're just finding extraneous solutions. All the solutions here are extraneous. So there's no solution. This one has the solution set is the empty set. Empty set. No solution. That's pretty much it for equations here, give or take. Let me shift over to inequalities. Inequalities a little bit fussier. All right. So here's the main thing. So let's let B be positive. All right. Then if we think about the absolute value of A being less than B, what would that mean? If you think about a number line, right? You think about B, you think about minus B, you think about B, right? What is this? In a sentence, what does absolute value of A less than B mean? This means, right, distance from 0 to A is less than B. You're at most B units from the origin. So that's exactly this, right? Because from the origin, you can go at most this be that way or be that way, right? The distance in both cases is B, right? Distance B to the right or to the left, but you're within B units of the origin. Like generically speaking, A, it's up in here somewhere, yeah? Or it could be over here, right? But the point is A has got to be, it's stuck between plus or minus B because of this distance statement. Is that reasonable? So in other words, what we have is that we have that minus B, right, is less than A is less than B in this case. All right? So just to summarize, we have the absolute value of A is less than B if and only if minus B is less than A is less than B. What if we're looking at greater than rather than less than? Is the story the same? Right? What if we have the absolute value of A is greater than B? What does that mean in a sentence? This means the distance, right, from 0 to A is what? Is more than B units. What does that look like on the number line? Well, basically you've got, so here's 0 in the middle, right? Let's say this is minus B and this is B. So to be more than B units from the origin, either you're to the right of B, like over here, right? Or you're to the left of minus B, like over here. So there are two cases. They're disjoint cases. Either your A is over here, or your A is over here, but they're not bounded by the same inequality at all. They're bounded by separate inequalities. The one on the left is bounded by A is less than minus B. On the right, we have that A is greater than b, right? And these are exclusive in the sense of it's either this one or it's that one. You can't have both. And so what I'm telling you is that in this case here, this discussion in summary gives us the following. It gives us that the absolute value of A is greater than B if and only if A is less than minus B, or A is greater than B. So let me put a box around these guys here, because we're gonna use these. These are our go-to these anchor the whole discussion going forward, all right? We're going to hang our hat on these. These are what we use to do problems, all right? Let me show you how that works. Let me show you how that works, right? So example, oh no. Well, I hope you get, what example were we on? I've erased it. 8. Thanks. So here's one. Suppose you're looking at like the absolute value, right, of 6x minus 7 less than 2. How do you solve this inequality involving absolute values? The answer is consult the boxes, all right? So I go, well, this is a less than problem, so I look at this, right? And I think to myself, I can think of A as being 6x minus 7, basically, right? And the pattern here, B is my what? B is like 2, yeah? So just use that pattern. So we got minus 2 is less than 6x minus 7 is less than 2. So we can unwrap an absolute value inequality, less than inequality, as a compound inequality. Notice that the absolute value is gone, right? Yep.
Did you get the -2 from this?
Yeah?
Saying that after you get out positive.
Mm-hmm. But it's this discussion. It's all this right here. This is how I got it. So I'm just applying this discussion to that case. I mean, this means that the distance of 6x minus 7 from the origin is at most 2 units, which means that this number, whatever it is, has to be between plus or minus 2. So now, hey, now we're back to like last class. We can solve those, right? So add 7 across the thing. That'll isolate my 6x, right? I've got 5 less than 6x less than 9. And then divide by by 6. And that will give us 5/6 less than x less than 9/6. 9/6, also known as 3/2, right? So what's my solution? Solution set is apparently 5/6 to 3/2. See? So these aren't bad. They don't have to be bad, right? Let's try example 9. Same expression. This time, we have absolute value of 6x minus 7 greater than or equal to 2. A little bit different, right? Greater than or equal to 2. So now that means that we're either going to have to solve 6x minus 7 less than minus 2, or 6x minus 7 greater than 2. Now, I allowed equality here. I guess I should fess up, guys. If I had equality here, then you just have to put it here and here. If I have equality here, it also goes here and here. Just think through it. Nothing terribly deep about that. So like in this problem, I'm looking for possibly equals, so I put equals here as well. In there. All right, so now we have two inequalities we have to solve. This time they're logically separate. The same x does not solve both of these, right? Like the x which solves this is not the same as the x which solves that. So we're using this notation x with the understanding that it's a different x here and here. If you were writing a computer program, you would want to use different variables for these two statements. In contrast, up here, if you were to separate the two inequalities that are here, right, which is minus 2 is less than 6x minus 7, and 6x minus 7 is less than 2, the same x works for both of those inequalities. They're jointly held. Not the case down here. Very different. Okay, so add 7, right? Add 7. This gives us 6x less than or equal to 5, or 6x greater than or equal to 9, which gives us x is less than or equal to 5/6, or x is greater than or equal to 3/2, which in terms of sets, this means x is an element of minus infinity to 5/6. This means x is an element of 5/6 is included, my bad. 3/2 to infinity. You can't have x in both of those at the same time. There's a gulf between them. Never the two shall meet. So the solution set for example 9 is minus infinity to 5/6 included, union 3/2 to infinity. This is a lot like a pair of examples I did last time. Remember, I think I did a pair of examples last time where it was the same expression, but one with greater than and one with less than. And we noticed that the solutions to those two problems were like complementary. Or did I not do that in here? Teaching 4 sections of this class is messing with my brain. So let me point out here that these solutions are complementary. So what do I mean by that? If you draw a number line, right? Look at this. So like 5/6 to 3/2, we could visualize like this. Right here, right? So this, my bad. It's supposed to be parentheses, right? So this is example 8 solution, right? Where is example 9 solution? See, the example 9 solution is at 5/6, right? On out, or at 3/2 on out, right? So if you put them together, you have everything. Right? Because 6x minus 7, it's either greater than or equal to 2, like in example 9, or it's less than 2. It's impossible for it to be anything else, right? Because the absolute value of 6x minus 7, whatever x is, it's definitely a number. Like the domain of absolute value of 6x minus 7 is a function, whatever that means. We'll talk about it next week. It's everything, right? So a lot of times I'll have a pair of questions like this on like a quiz or a test. You might think, did this just ask this question? Well, if you have that feeling, there's probably a distinction. Then probably the distinction is that one was less than and one was greater than or equal to. Now, if you view these problems as a package deal, you can use one to correct